In this video, we're going to look at how we can solve differential equations that aren't separable and don't have a nice substitution that we can do to make them separable. So specifically, we're going to look at equations in the form dy dx plus some function p of x times y equals some function q of x. And we're saying that q of x does not equal 0 because if it did, it would actually just be a separable equation. So we're going to find an integrating factor by first solving that separable equation, dy dx plus p of x times y equals 0. So you can see the solution here. I'm just separating the variables. It ends up giving me that y equals e to the power of an antiderivative of p of x. That is what we call the integrating factor. And in fact, as we go through this process, absolutely any antiderivative of p of x will work. So we're going to use the one where c equals 0. And in fact, we're going to just use where instead of having the negative there, we have a positive. Because like I said, any antiderivative will work, and this ends up working as well, so it's easier. So we're going to do it that way. So now we're going to go back to our original differential equation. And what we're going to do is we're going to multiply through that whole differential equation by this integrating factor. So we get e to the power of that antiderivative of p of x dx, dx dy, plus, I'm going to write this in this order, p of x times y times e to the power of the antiderivative of p of x dx equals q of x times e to the power of the integral of px dx. So I've just multiplied every term in this equation through by that integrating factor. Now, just to make this a little bit easier to look at, let's let the derivative of some function h of x equal p of x, so that we can just replace h of x is going to be that whole integral of p of x dx, so that I don't have to keep writing that every single time. So what we now have is e to the power of h of x dx dy, or dy dx. Oops, that's not what I wrote up here. Let's fix that. Or not. All right, so we have p of x times y times e to the power of h of x equals q of x times e to the power of h of x, recognizing that h of x is some antiderivative of p of x. Now, what this gives me, actually, I can do a different substitution in here as well, because I know that p of x is a derivative of h of x. So what I'm actually going to do is I'm going to replace that with h prime of x. So what I now have on the left side of this equation is a product rule. This is the product rule for the derivative of y times e to the power of h of x dx. Because what I have in the first part, I have just e to the power of h of x times the derivative of y. And I have, so that's that part, the derivative of y. And then I have y times the derivative of e to the power of h of x, which would be e to the power of h of x times the derivative of h of x. So this is the product rule for that. So in other words, I can just simplify that whole side of the equation and write it as the derivative of y times e to the power of h of x dx equals some function of x times e to the power of h of x. This is now separable. So this is separable. Well, it's not separable per se, it's integrable. So if I integrate it, what I get, so I can multiply the dx over to the other side, that's sort of why it is. So I get y times e to the power of h of x equals the antiderivative of q of x e to the h of x, which is all just expressed as a function of x dx. So that makes that basically solvable. Now, let's look at that in practice. So what we're keeping in mind is that we are essentially, this integrating factor thing is the opposite of the product rule for differentiation. Substitution was an opposite of the chain rule when we were integrating. This one is the opposite of a product rule. All right, looking at an example. So I have, in this case, on the left-hand side of the equation, my p of x, as it were, is 1 over x. And my q of x is x squared. So p of x is 1 over x. Now I wanted h of x to be an antiderivative of that. So ln of x. And I'm not going to worry too much about the absolute values here. That's a nuance we're not going to get into. So the integrating factor is going to be e to the power of h of x. So e to the power of ln of x, which is just x. So the integrating factor in this equation is simply x. And I'm going to multiply through the entire equation by that. So I get x times dy dx equals y over x times x, oh, not equals, sorry, plus y over x times x is just y, so plus y, equals x cubed now. Well, on the right-hand side, so I have a function of x. On the left-hand side, I have what would happen if I was deriving xy with respect to x, because I would multiply x times the derivative of y, and then I would add y times the derivative of x, which is just 1. This means that my equation now becomes the derivative of xy with respect to x is x cubed. Or, in other words, xy is the antiderivative of x cubed dx. Well, that's easily integrated. I get xy equals x to the power of 4 over 4 plus some constant. It's important that I add the constant here because now my next step to isolate y is to divide by x. So I get x cubed over 4 plus whatever that constant was over x. So it's not just a constant term anymore. And that is the general solution to this differential equation. So that's the basic principle that I have going on here. Obviously, it gets a little more complicated if my integrating factor is something more complicated than just x. So let's look at another example where we have a bit of a messier situation. So in this case, p of x is the entire function of x that's being multiplied by y. So what's important to note in the second term here is I have negative x over x squared plus 1 being multiplied by y. So p of x is negative x over x squared plus 1. H of x has to be an antiderivative of that. So that's not quite as obvious and nice as it was in the previous case. But h of x is an antiderivative of negative x over x squared plus 1 dx, which isn't too bad as these things go, because a simple substitution will get us there. So if I do a substitution where u equals x squared plus 1, then du equals 2x dx, which makes this equivalent to negative 1/2 1 over u du, or in other words, negative 1/2 ln of u, which in this case is actually negative 1/2 ln of x squared plus 1. Now, even if I had put the absolute value on the u, I definitely wouldn't need it here. So that means that my integrating factor is going to be e to the power of this. So e to the power of negative 1/2 ln of x squared plus 1, which using the log law to put the -1/2 inside of the natural log, and then combining the fact that I have e and ln there, this ends up being 1 over the square root of x squared plus 1. So that is the integrating factor here. So I'm going to multiply through the whole equation by this. So I get 1 over square root of x squared plus 1 times dy dx minus x over x squared plus 1 times 1 over the square root of x squared plus 1 times y equals, well, handily over on the right-hand side of the equation, the square root of x squared plus 1 cancels, and I just get 1 over e to the power of x, which I'm just going to write as e to the power of negative x. If you take the time to confirm, you can, but this is what the derivative of y over the square root of x squared plus 1 with respect to x looks like, using the product rule, basically, or you could use quotient rule. You're going to end up in the same place. So that means that y over the square root of x squared plus 1 equals the integral of e to the power of negative x dx. Well, that means, which is just negative e to the power of negative x plus some constant. So when I multiply through by x squared, square root of x squared plus 1, I get y equals the square root of x squared plus 1 times, I'm going to write this as a constant minus e to the power of negative x. I mean, there's a chance the constant is negative, but you know, that's still my situation here. All right, one more example together. And this one we have an initial condition. This one, our p of x is a little bit simpler. P of x in this case is just -1, which means that h of x, which is an antiderivative of that, h of x is simply negative x. And that makes our integrating factor e to the power of negative x. So when we multiply this all the way through, we've got e to the power of negative x times dy dx minus e to the power of negative xy equals, well, e to the power of x sine x times e to the power of negative x, handily the e to the power of x and e to the power of negative x cancel out, so we just get sine x. On the left-hand side of this equation now, that is the derivative of e to the power of negative x times y with respect to x. You can verify that by deriving that function again, if you so choose. And that means we have now e to the power of negative xy equals an antiderivative of sine x dx. Well, the sine of x dx has an antiderivative of negative cos. So e to the power of negative xy equals negative cos x plus some constant. We can actually figure out what that constant is because we do have an initial condition here. So e to the power of -0 times 1 equals negative cosine of 0. Oops, I already wrote the constant. Plus a constant. I gave you a little sneak preview here. By accident. At least I'm pretty sure that's what the constant is. My subconscious was telling me. Okay, so e to the power of -0 is 1. So that's 1. Cosine of 0 is 1, so that's -1 plus c. So yes, surprise, c equals 2. So this now means that my equation, when I plug that in, I get e to the power of negative xy equals negative cos x plus 2. I'm going to switch the order of that. So when I divide by e to the power of negative x, it's the same as multiplying by e to the power of x. So I've got e to the power of x times 2 minus cos x is the specific solution to this differential equation. All right, so you might need to, go back over some of those examples a little slower, a little take time to check that the derivatives are what they are. But you can also practice these. So in your PDF textbook, section 5.3 solves equations using integrating factors. And questions 11 through 18 on the differential equations worksheet are also integrating factors questions.